Genome science will have a real impact on all our lives, and even more, on the lives of our children. It will revolutionize the diagnosis, prevention, and treatment of most, if not all, human diseases.
You're listening to Stereochemistry. I'm Matt Davenport, and yes, that was former U.S. President Bill Clinton. We're listening to him because, well, I'll let CNN senior correspondent Lisa Jarvis explain why. Hey, Lisa.
Hey, Matt. And I definitely will explain, but could you finish the quote first?
Oh, yeah.
In coming years, doctors increasingly will be able to cure diseases like Alzheimer's, Parkinson's, diabetes, and cancer by attacking their genetic roots. In fact, it is now conceivable that our children's children will know the term cancer only as a constellation of stars.
That was a press conference in June 2000 to announce the completion of the mapping of the human genome. To get nitpicky for a minute, the genome wasn't fully 100% mapped until 2003, but they had figured out the most important bits by 2000. At that time, researchers thought knowing a person's genetic blueprint would tell us everything we needed to know about the proteins in a person's body that malfunctioned in a disease, and that those proteins would lead us to treatments. But we're now 18 years out from President Clinton's press conference, and, well, there's still a lot of work left to do. None of those diseases that he ticked off has been cured. There's a whole host of reasons we haven't cured all diseases. Understanding the complex biology of various diseases has been hard, and doing the chemistry to make drugs that safely and effectively promote healthy human biology, also super hard. Even in this era of rapid and affordable genome sequencing, we still come up against one big problem. Knowing the genetic driver of a disease, say a certain type of cancer or an inherited neurological condition, does not mean we know how to develop a treatment for the disease. Most conventional drugs, small molecules and antibodies, target proteins to treat diseases. It turns out that there's a ginormous swath of proteins that conventional drugs simply can't access. Depending on who you ask, that swath includes up to 85% of our proteins. Scientists have a name for this hefty chunk of the human proteome, quote-unquote, undruggable targets. This episode of Stereochemistry is all about the undruggables. Remember, they're proteins we can't drug now, so undruggable targets present a huge opportunity for biotech companies and investors. In the last 2 years or so, people have poured hundreds of millions of dollars into firms developing molecules to drug the undruggable. These companies are taking a range of approaches, but they're all making some version of the same claim, that they will be the ones to first defeat the undruggables.
Coming up, we're going to explore why some drug targets are so darned vexing. And of course, we'll look at some of the chemistry that could finally crack these targets. Lisa spoke with researchers from industry and academia to learn what they think are the most promising approaches, from drugging the machinery that makes the proteins to better understanding the proteins themselves. And be sure to stick around till the end of this episode when we will unveil the very first installment of the Stereochemistry Book Club. Lisa will be joined by a special CNN guest to discuss the book that is taking the biotech world by storm, John Carreyrou's Bad Blood. But first, Lisa, I have to ask, how can people spend all of this time and money going after these targets while at the same time refer to them as undruggable?
Good question. It turns out to be a word that elicits some pretty strong reactions.
I hate that term. I've hated it for the last 10 years.
So I don't like the word because I think it's a self-fulfilling prophecy. If you think it's undruggable, you don't try to drug it.
I think 50, 100 years from now, there will be no protein that is undruggable. Everything will be druggable.
Okay, so undruggable isn't everybody's favorite word, and many agree on their dislike of it. Some prefer recalcitrant, others say intractable. Some just refer to difficult or tough targets. Whatever we call them, researchers agree that we probably want to shrink down our definition of undruggable from the general 85% of the human proteome that we currently can't access to focus only on the portion of the proteome that's worth chasing. As one researcher told me, we need to focus on the things that are desirable to drug, not just difficult to drug. The next general point of agreement is what it means to be difficult to drug. Actually, let's back up a minute and talk about what makes something easy to drug, or at least what's possible to drug. So far, most drug design success stories have targeted molecules like membrane receptors, kinases, or other enzymes that are in the business of binding ligands. Those targets tend to have nice, well-defined pockets for ligands to nestle into. Chemists have gotten really good at designing therapeutic compounds that can park in these pockets like the natural ligand. It's when proteins lack an obvious toehold that researchers start sweating. That's when a protein can look undruggable. No target more aptly fits into that undruggable description as the one that tops basically every drug hunter's wish list.
I usually immediately think of KRAS?
Yeah, I would start with KRAS.
My personal nemesis target is KRAS. Did you watch Star Trek? I don't know if you remember the Borg ship. There is no place to get into the ship. There is no receptor site for a small molecule on the surface of KRAS.
So KRAS is one of the most commonly mutated proteins in cancer. Researchers are confident that if they could just block its activity, they would be able to help a lot of people. Yet, it seems to be the perfect prototype of the undruggable protein. Chemists have been working on defeating that cancer villain for a good 35 years. With conventional chemistry not really panning out for undruggable targets like KRAS, people started looking beyond small molecules to things like gene and cell therapies and oligonucleotide drugs. But suddenly, small molecules are making a comeback. I asked Michael Gilman, a serial biotech entrepreneur who is currently CEO of not one, but two companies, to tell me why small molecules are falling back into favor.
We know there's a lot of value in new biology, right? Biology that's outside this fairly circumscribed area where small molecules work. And in order to access that new biology, we've had to go to new therapeutic modalities. Those therapeutic modalities are not completely well understood, right? I mean, they're still pretty risky. They're complicated to work with.
Mike also points out that many decades of experience with small molecules put some certainty into the process for scientists, for regulatory authorities, for doctors, and for the people taking them.
So first of all, we understand how to make small molecule drugs, right? We know how to develop them. They're generally predictable, and, we know how to flush out their unpredictable behaviors. We know how to manufacture them. We know how to formulate them. We know how to get them to your local pharmacy, right? I mean, it's a very, very well-oiled machine, medicinal chemistry. And so that's why I think there is a strong incentive to figure out how to move small molecules into these new areas of biology that until recently were not thought to be accessible with small molecule chemistry.
At the same time, the business climate has never been more supportive of early science.
I think that there is also a market pressure right now. There's so much money out there that this amount of money in biotech, it's unprecedented.
That's Rosanna Capeller, another biotech entrepreneur. She compared KRAS to the Borg ships earlier. Rosanna has helped start and then led research at several companies. Most recently, she was a chief scientific officer at Nimbus Therapeutics, a Boston-based biotech that uses advanced computational chemistry to try to find vulnerable spots on difficult targets. And she also sees a more basic reason for scientists coming back to try to conquer undruggable targets with small molecules.
I think, honest to God, human curiosity. I think it's like going to Mars. If you have the technology to do that, why not do it? In the past 20, 30 years, the technology has evolved a lot. So, for example, at Nimbus, we went after targets that were very well known. We knew that there would be an impact, but we didn't have a way to make small molecules against those targets. And computational chemistry finally reached a tipping point that could really help us discover new chemical entities.
And this evolving technology, not just computers, but tools like cryogenic electron microscopy, room temperature crystallography, advanced mass spectrometry, and others, has reshaped the way scientists think about what's going on inside cells.
For the last 20 years or so, our sort of conception of drug design for proteins has really been driven by crystal structures, right? And crystal structures are completely static, and they've been helpful. But I think that the reliance on crystal structures has really fixated in people's mind that proteins are static targets, and they're not.
It turns out that proteins twist and flex and jiggle. They can be wildly unstructured or amazingly compact. And Mike points out that proteins don't exist on their own as a static target like those lovely 3D structures scattered throughout academic journals. They're in an intricate dance with a whole host of partners inside cells. Advanced microscopy, more powerful computer modeling, and other tools are allowing researchers to record that dance, revealing hidden nooks and crannies for tethering small molecules. Chemical biologists have come up with clever ways of mapping out the surface of proteins to find all of the places a molecule could bind. Meanwhile, chemists have upended the way we think about how a small molecule drug behaves and what it can do to fight disease. For an example of that, let's look at what Mike's company, Arrakis, is doing. The company is developing small molecules to bind RNA, which shuttles the recipes for building proteins. It's an idea that many would have considered kind of bonkers at one point.
Just like there has been sort of a conventional view that small molecules can only drug certain kinds of proteins, there has been a similarly widely held view that you can't really bind RNAs with small molecules because, number one, they're not really structured like proteins are. And secondly, to the extent that they have structure, the pockets are sort of uninteresting to small molecules. And, it turns out that neither of those things are true. And in fact, we take a lot of drugs that bind RNA. A lot of the antibiotics bind bacterial ribosomes. They bind the RNA. They don't bind the proteins. They actually bind the RNA.
Of course, those drugs were not intentionally designed to bind RNA. Researchers just sort of lucked into them. But companies like Arrakis, where Mike is CEO, think they figured out how to use small molecules to wrangle RNA into submission. Mike gives the example of messenger RNA, which tells ribosomes how to make proteins. Before the RNA can pass along those instructions, it's folding and refolding into a bunch of different structures with different shapes, none of which can pass on protein-producing instruction.
Sort of any one of those structures is an opportunity to trap that RNA in a non-productive state. And so that's kind of how we're thinking about the problem.
So, that's one way to beat an undruggable protein. Keep it from ever being made. When we come back, we'll learn about more strategies looking at directly targeting proteins themselves.
We all know that being a chemist is a pretty great way to make a living. So wouldn't it be great if there were an easy way for chemists to find that next great employment opportunity?
Well, I've got some good news for you, Matt.
Well, if it isn't recruiting advertising product manager, I'd rather. Tell me more about this good news.
Yeah, did you know that CNDN has its own job board?
I did not know that.
Well, we do. You can go to cenjobs.org to find the latest chemistry openings. You can upload your resume so that employers can find you. You can create job alerts so that you're emailed relevant jobs automatically. And if you're an employer, you can post your openings for 30 or 60 days.
So what's been your favorite part about working on the job side of things here?
So I really love connecting employers with job seekers. I feel like I'm making a difference for chemists out there.
Have you guys had any success stories? Have you had people reach out to you, let you know that they found their job through CNDN Jobs?
We haven't had anyone reach out, but I think this is an excellent opportunity to let your listeners know if you have found your job through the CNDN Jobs job board. Let us know and we'll give you a shout out.
Send us an email at cen_multimedia@acs.org if you've got a CNDN job success story to share with us. And if you're looking to find or share a chemistry job, visit cenjobs.org.
At any given moment, the levels of hundreds of proteins in each cell of your body are being fine-tuned by transcription factors. Transcription factors are proteins that convert DNA into RNA, turning genes on and off. Transcription factors make sure enough of any given protein is being expressed in a particular cell, in a particular tissue, at a particular time. Yeah, they're pretty critical. And pretty undruggable. After KRAS, the next top target on everyone's drug discovery wish list is a transcription factor called c-Myc. C-M-Y-C. In cancer, it's sort of stuck in an on position, promoting a whole bunch of genes, including some that allow cancer cells to multiply. But there are transcription factors beyond c-Myc worth targeting. Here's MIT professor Angela Kohler.
I can't tell you how many group meetings I attended focused on genome-wide association studies for a whole host of diseases, not just cancer, but a whole host of diseases where transcription factors would often come to the top of these lists. However, as a community, we would always say, well, these are undruggable targets. When you purify these proteins away from their partner proteins, they tend to lack shape. So as a chemist, it's almost impossible to think about how would you design a small molecule against a protein that completely lacks shape?
Angela has spent a decade focused on solving that problem. Her lab uses something called small molecule microarrays to sweep for molecules that bind to a protein of interest. Her team essentially washes a fluorescently tagged or epitope tagged version of the protein over a surface that's dotted with thousands of small molecules. Anything that sticks lights up. For tougher proteins, like transcription factors, the researchers wash the fluid from a cell's innards across the microarray and run the same type of experiment with the proteins expressed by the cell. Researchers can winnow out the hits by tagging the proteins with probes that fluoresce or show up in NMR spectra. That method lets Angela's lab capture small molecules that bind to the protein in a more real-life setting, mid-dance and with relevant partners nearby. By combining that with a functional assay, a test for whether a small molecule is affecting the activity of a transcription factor, Angela's lab has been able to come up with several intriguing chemical probes against tough targets. Now, probes are not drugs. They're tools chemists use to explore biology, but often help foster drug design. In fact, Angela's work recently became the basis of a company, Kronos Bio. Another technique that has people really excited is called activity-based protein profiling, which allows researchers to map out all the cracks and crevices in proteins. Scientists use chemical probes that react with amino acids, either in active sites or in other types of binding pockets that dangle off proteins, so that advanced mass spectrometry can be used to pinpoint where the probe has attached itself to the protein. I'll let UC Berkeley professor Dan Nomura, one of several chemical biologists using the method, explain more.
A lot of these proteins tend to be disordered, and so it's not really clear whether any molecule can actually fit into a binding pocket that's inherently disordered. The way that these mass spectrometry-based approaches work and the way that our chemical probes work is that we don't really have to know the structures of these proteins up front. We can just throw in our probes, see where they stick, and then use mass spectrometry-based approaches to identify all the sites where they did stick. We and others in the field, we've now been able to identify over 100,000 druggable hotspots across over 20,000 protein targets. This is now a potential way in to be able to at least develop a small molecule ligand against any protein target within the proteome. And whether that's functional or not is a different story.
What Dan means by that last bit is that many of the sites that this mapping reveals are inactive. A small molecule can bind there, but it can't turn the protein on or off. For the handful of sites that turn out to be active, great. The next step is to follow a conventional drug discovery campaign. Try to design a molecule that fits into that pocket. And in fact, Dan's lab has expertise in designing covalent inhibitors based on the active sites they find. But there's still value in molecules that bind to but don't affect the function of a protein. Those molecules can be starting points for a hot new area of drug discovery squarely focused on undruggable targets, protein degraders. Protein degraders work not by turning off an errant protein, but by getting rid of it altogether. These small molecules feature one end that binds to a bad-behaving protein without changing its function, and another end that binds to a compound that, through a series of events we won't get into here, causes the protein to be sent to the proteasome, otherwise known as a cell's trash compactor. The cool thing is that after the protein's been trashed, the degrader can move on to do the whole thing over again. They're catalytic. On the face of it, these protein degraders are rather unlikely looking drugs. They're kind of long and floppy and they weigh a lot more than a typical drug. And that catalytic part, that's pretty unusual. In the lab, at least, researchers have shown that it doesn't take too many protein degrader molecules to break down a whole bunch of proteins. In the past 2 years, nearly every big pharma company has begun to work on protein degradation, and several biotech companies have launched with efforts focused on protein degraders. Still, it's important to remember, none of these efforts has taken down an undruggable target in a human. Not protein degraders, not small molecules that target RNA, not a whole host of other things we didn't even talk about. Lots and lots of time and effort and money is going into changing that, and we might even see the first clinical trials for some of these new approaches in the next year. But right now, it's all theoretical. But let's for a moment assume that one of these things, hopefully more than one, is going to work. I have to wonder, what happens when we finally get to one of these classically undruggable targets? Let's consider the cancer villain that tops everyone's list, KRAS. Many groups inside academia and industry are working on that target, and it's reasonable to expect small molecule KRAS inhibitors will finally make it into human trials soon. With so much known about the importance of that target in cancer, expectations are pretty high. So, what would a successful trial look like when you drug the undruggable? UCSF's Keyvan Shokat, who has spent a good chunk of his career working on KRAS, has some thoughts on that.
It's funny, I actually think it would be great if all of the normal things start happening for the KRAS drug.
That means some patients will respond dramatically, others won't. Some might be resistant. Basically, even though the new drug is fueled by brand new chemistry, you want the resulting biology to look like the drugs we already understand.
You want the first drug to hit that undruggable one to actually not be giving you completely new biology. That would be worrisome. I think taking an undruggable protein and making it a traditional drug discovery program, that is a huge accomplishment.
So the moment is finally here. We're launching what we hope will become our first somewhat regular podcast segment, the Stereochemistry Book Club. Lisa picked the book this time around, but we want your help in the future. So tweet at us or email us at cen_multimedia@acs.org if there's a book you think chemists should be reading and talking about. I'll let Lisa introduce her selection, Bad Blood, in just 1 second. But of course, she needed somebody to talk about the book with, and when I found out it wasn't about vampires, I was out. Which means we have another first for the podcast that we're very excited about. You'll be hearing from our very own Ryan Cross, Science Boss. So I'll turn the mics over to them now, but you might want to put on your oven mitts to make sure you can handle their hot takes.
In the last few minutes of this week's episode, I wanted to talk about a book that I suspect nearly everyone who's interested in biotech is reading, has read, or is feeling left out because they haven't read. Bad Blood by Wall Street Journal reporter John Carreyrou. It's a captivating story of the spectacular rise and fall of Theranos. Many of you probably know of Theranos as the Silicon Valley blood testing firm started by Elizabeth Holmes, who convinced a legion of wealthy and connected people that she had invented a machine that could quickly analyze a drop of blood for hundreds of different health markers. At one point, Theranos and Holmes were worth billions. This created what's known in business circles as a unicorn, a privately held company worth more than $1 billion. If you haven't read any of the many think pieces on Holmes or Theranos, spoiler alert, her invention was basically a sham. Theranos scientists were never able to get their blood reading device to work on such tiny samples. Meanwhile, she just kept on making deals as if everything was fine. So Bad Blood is Carreyrou's account of how Theranos came to be and how his reporting basically took the company down. To talk about the book, I'm joined by CNEN biotech editor, Ryan Cross.
Hey, Lisa.
First, I have to ask what you thought, Ryan. Did the book live up to the hype?
I think so. This was a really gripping nonfiction drama. And the last 100 pages or so of the book, once the author enters the story, I thought were just fantastic. It's a little light on the science, but so was the company, so I guess that's to be expected.
Yeah, I have to say I had the same experience. So what happened is that the first 2/3 of the book, you're hearing about how the company came to be, and it's told from the perspective of, many different people who worked there. I think he interviewed something like 150 different people for this book. And then the last third of the book, the reporter himself enters the scene. And it went really fast at that point because, of course, he was there and is able to provide a different kind of color. We should note that Carreyrou never was granted an interview with Elizabeth Holmes or any of her key people in her company. And I will say that I think that he got the story and was able to be so tenacious because he was never drawn in by whatever persona she had. But at the same time, one thing that I really wished was to be able to understand when she started being a deceitful person. Was she just born that way? Did she start this company and start to get attention and feel like she had to keep it up? Like, what happened, with her? What happened in her life that made her able to do this? But yeah, it was pretty gripping. So I guess I wanted to go to what was the most bonkers thing you read in Bad Blood?
Yeah, it's very hard to just pick a single thing. But I think one of the craziest actually happened at the start of the book. Theranos wanted to put their blood testing machines in people's homes so that pharmaceutical companies could monitor reactions to experimental drugs. And when they were giving a demonstration of how their device worked to Novartis, they completely deceived the company and used pre-recorded results since their machine wasn't always working. And when one of the business partners at the company said they should stop doing these demos if they weren't completely real, Elizabeth Holmes told that guy he wasn't a team player and fired him on the spot.
I mean, almost every page something happened that made your eyes pop out of your head. They talk about how there's this thing called the CLIA certificate that you need to be able to operate as a blood testing company. And so the California Department of Public Health inspector came to certify the company, and they had a secret lab where they had their proprietary devices that did not work. And I mean, essentially, they completely deceived this inspector who came to visit. She arrived and never saw the lab with their proprietary devices. I mean, it was, to me, some next level fraudulent behavior. So one of the things that I wanted to talk to you about, Ryan, You and I both cover biotech and CNN, and we often write about these companies that are launching. Often there's not a lot of information about the science that they're doing. And I'm reading Bad Blood at a time where there is some criticism about that type of coverage. You know, how much ink should we be giving to these companies just because they're raising a lot of money? How do we decide that there's a there?
Yeah, you're right. We see these large financings a lot now. And there also seems to be a trend for these companies to not disclose even the diseases or drug targets they're working on, yet alone how they plan to tackle them. I think what's interesting is that this company, a lot of people don't know this, but they were founded a while back in 2003. And it really wasn't for 10 years before they started to get a lot of press. I think after 10 years, if a company still doesn't publish scientific papers and still refuses to talk about their technology in any depth, I think that would be a red flag. And unfortunately, I think this problem actually might get worse, especially as big data biology continues to mature and as lingo like artificial intelligence and machine learning is used more and more to describe what companies are doing. There's sort of a black box that's hard to penetrate.
Yeah, I think one red flag for me is always when you see the same collection of scientific founders that have founded lots of other companies. And it's not that I think there's nothing there, but there's less often in those situations, say, scientific publications to pin a technology to, or some kind of foundational work that you at least can look at and understand.
Speaking of scientific founders and scientific advisory boards, though, something that is so perplexing to me about the Theranos story is their lack of of external scientists that were involved in the company. What did you think of the interesting cast of characters that were supporting the company with no scientific background?
Yeah, I mean, it is bizarre. Here is a collection of people that are very clearly connected to Elizabeth Holmes personally or through some family connection or friend of a friend connection, and they have no scientific basis for analyzing the company's technology. It was fascinating to me that was somehow perceived as a positive. I mean, of course, big pharmaceutical companies have people from other industries on their boards who might have perspective on how to run a big business. But, you still have a scientific advisory board. You still have people who bring kind of both a business and science perspective to the table. Whereas this was fully... I don't know. I would not have looked at that board 10 years ago or 5 years ago and said, oh, yeah, that's a reason I should write about that company. I believe what they do. One of the reasons I wanted to talk about this idea of when we do and do not choose to write about young companies is that, of course, this entire segment that you guys just listened to was about companies that have yet to produce a drug. They haven't put a drug in the clinic. They're working on technology that's unproven, but this is the area that we cover. And so I think there's been a lot of internal discussion after the Theranos blow up about making sure we have a healthy level of skepticism and also are trying to temper how we write about these technologies, that they're not going to cure cancer, for example, but that they're early and have promise. It's a difficult balance, I think.
Yeah, I think it is too. And I think for us, sometimes it is still a story to write about, some of these young companies that are kind of secretive, just for the fact that, it's showing that somebody is investing, $50 million or whatever the number is in a certain area that maybe hasn't got a lot of attention yet. So, and I think that's exciting for certain scientists in those fields to see, the disease I work on or the area that I work in is attracting commercial interest. But I do think we have to be very, very careful in, pointing out the limitations and the long timelines before that research will be turned into a medicine to help people, if ever.
One thing that I did want to ask you about, there's been a lot of comparisons made between Elizabeth Holmes and Martin Shkreli, who is known publicly as the pharma bro. And he is, of course, the former CEO of a company called Turing Pharmaceuticals that had bought this drug and jacked up the price by 5,000%. And ultimately went to jail, not for that, not for the price gouging, but for some kind of shady financial things that he did to cover up losses at his hedge fund. So I don't know if you have any thoughts on kind of why it is that Martin Shkreli rose to this public imagination, like pharma villain, whereas Elizabeth Holmes has kind of, I don't know, it feels like flown under the radar a little bit. People don't seem as bothered by what she did.
Yeah, that's a really good question. And I don't know if there's a simple answer, but clearly bad behavior is in the nature of both of their characters. Although between the two, undoubtedly, Elizabeth Holmes has a penchant for playing fast and loose with the law. The number of times that, she lied and tried to jump through loopholes that may or may not have actually existed in the book was quite striking.
One thing that strikes me when I think about Shkreli versus Holmes is it felt to me like he may not be a guy anyone likes, but the illegal activity he participated in was a panic move to cover up the loss at his hedge fund, and that was sort of an isolated incident and was more of a bug, not a feature of his personality. But it felt to me more that Holmes lying and being deceitful and delusional was more of a feature than a bug. I hope someday someone has the story of kind of how she got to be like, who is Elizabeth Holmes in high school? Did anyone think that she had the capacity for this level of a 10-year charade? I would love to understand that. Okay, so Ryan, if we're rating this book out of 10 unicorn tears, where do you think Bad Blood falls? Would you recommend this to other people to read?
Yeah, I would. I'd probably give it 7, maybe 8 unicorn tears. It was a great book. Definitely a must read for anyone interested in biotech. And, I'm even considering recommending it to some of my non-biotech friends so they can sort of see what the inner life of that world is like.
Yeah, same. I think I also would give it 7.5 to 8 unicorn tears. My one critique, which was not a reporting issue, but an access issue, was not understanding what set Elizabeth Holmes on this path, which wasn't really what the book was about, but I still wished that was something that I would understand at some point. But it is a deeply reported, fast-paced, affecting book. I loved it and would definitely recommend it to biotech and non-biotech friends alike. So, 2 updates since Ryan and I recorded our chat. The first is that in a recent interview, Carrie Rue said that Holmes is currently pitching investors on a new company idea. Bananas. The second is that Holmes now faces criminal charges for wire fraud. She might not quite have escaped jail time yet.
Thank you so much for the update, Lisa, and for this entire story. It was awesome. Is there anything else you'd like to say to listeners before we sign off for the episode?
I'd really love to hear from listeners about what book we should read next. And if you know any company you think is the next Theranos, drop us a line. We'd love to write about it.
If you would like to drop said line on Twitter, Lisa's at Lisa M. Jarvis, Ryan's at RLC Science Boss, and I'm at Mr. Matt Davenport. Or feel free to email us at cen_multimedia@acs.org. And be sure to tune in next month when Stereochemistry heads to Germany to witness the science power of the now operational European X-ray free electron laser. To make sure you don't miss it, subscribe to Stereochemistry now on iTunes or Google Play. And one quick programming note. We'll be taking a short summer break in July. We'll still have an episode for you, just look for that the week of July 25th. Right now, you're listening to Soundboy by Abstracker, and the music you heard during our piece about CNM Jobs was The Confrontation by Poddington Bear. And the music right before our first Stereochemistry book club was The Ascent by A.A. Alto. And we're starting to share additional resources and links for our podcast episodes on our website, cen.acs.org. Be sure to check that out and let us know what you think. This episode was written and hosted by Lisa Jarvis and produced by me, Matt Davenport. Thanks for listening.